So this was work actually that was done several years ago, as part of my graduate program with Dr. Dave Huggins. This work was funded by the Washington Grain Commission, and I really want to make sure to highlight that because of the importance of our regional commissions in funding work that's important to growers in this region. So really working to serve the growers and the ag community of this region is a big part of what we've been working on with the PNW Farmers Network in collaboration with the USDA LTAR site here in Pullman and the greater region. Also, some of my work is funded by Western SARE. So they are such a great organization, and we always got to give them a shout out when possible. So if you are not one of the folks who receives all of the PNW Farmers Network newsletters as they come out, please do find us online, on YouTube, on Twitter or X, and feel free to email me if you'd like to be on the newsletter, or if you have any questions or comments about how we can better work together to serve this region's ag community. With that, let's get started talking about Lyme program management in the Inland Pacific Northwest. As soon as I can, there we go. So what I'll be talking about is key elements of Lyme program development. So the first step in that is to understand soil acidity, why amelioration is an important part of that process, and better understand or make sure you're understanding your management goals and how that all fits together when you're developing your amelioration or remediation program. So of course, as a soil scientist, soil testing is always the right answer. But soil testing also helps us understand how much lime to apply. And then we'll talk a little bit at the end about what and how to apply in terms of product selection. Again, that will not be a comprehensive overview, but we'll get the conversation started so that we can keep continuing it during other parts of this workshop series. So we're going to start off by referring back to this video series. So it's a 3-part video series on soil acidification. Each video is about 5 minutes. So one of my favorite ways to best understand invisible chemical processes that are happening in the soil is with cartoons. So this was a really fun effort to put together a couple of cartoons that, again, kind of build on some of what Doug was introducing in the previous talk. So let's get started by just talking a little bit about, or letting this video briefly describe a little bit more about that negative log of hydrogen ions and how that translates into our pH number values.
pH measures acid or alkaline properties in a solution by determining the concentration of hydrogen ions. pH is described using a negative logarithmic scale. Neutral pH is 7. This is where the number of hydrogen ions and hydroxide ions are equal in solution. As each unit of pH goes down, the concentration of hydrogen ions in solution increases tenfold, making it more acidic. In agricultural soils, a pH below 5 is considered to be very low. If a base like calcium carbonate is added to the acidic solution, calcium is released while the carbonates combine with hydrogen ions, creating water and releasing CO2 gas. Decreasing the hydrogen ions concentration means the solution becomes less acidic. If the hydroxide ion concentration increases, pH will go up and the system becomes more alkaline.
So hopefully that was, like I said, kind of who doesn't like to learn through cartoons, was the thinking in that inclusion in that video series. So again, those videos can be found in the soil acidification resource collection on the WSU Wheat and Small Grains website. So thanks for that thumbs up, Doug. Do you learn through cartoons too? All right, well, I've got another one for you as well. So we'll just jump right into that because that actually talks more about why is the soil acidifying in this region. And again, this should build on some of what was already discussed. And then we'll get into the next steps. Oops, not yet. Here we go.
Soil forming factors strongly influence susceptibility to acidification. Climate is a driver of natural acidification. High levels of slightly acidic precipitation leach alkaline cations like calcium and magnesium out of the root zone. Calcium and magnesium are also taken up by plants and removed with harvest and residue. These effects accumulate over time, lowering soil pH and reducing the soil's ability to buffer against pH changes. Land management decisions also affect the rate of soil acidification. In agriculture, when commonly used ammonium fertilizers are applied, soil microbes convert the ammonium to nitrate, contributing excess hydrogen ions to the soil. Adding high quantities of ammonium fertilizer results in more hydrogen ions. The hydrogen ions accumulate, lowering soil pH and accelerating soil acidification.
So hopefully you all found that as fun and informative as I did in the effort to develop that way of just talking again about this very, when we talk about land degradations facing the Palouse, and the greater Palouse region or the inland Pacific Northwest, like the Washington Soil Health Initiative did identify in its roadmap that erosion and soil acidification are two of the predominant threats facing this area. And both of them are very unfortunate, and appreciate that everyone is here today to be thinking about acidification as and how to work together to address that in this region. But one of the things about erosion is it's tragically visible, while acidification is much less so. So again, it's fun to make cartoons about that. Hopefully we'll get a chance to roll out some more of those through the Farmers Network in the upcoming season. So keep your eyes out for that. And we'll start talking more about effective liming. So effective liming increases soil pH. And of course, it wouldn't be a soil acidification or soil pH talk without this figure here. I like this one because it not only shows the way nutrient availability is reduced with declining soil pH, but also how aluminum becomes more freely available in the soil below pH 5, and how microbes do tend to find those acidic conditions to be less favorable. So when you do increase your soil pH, you optimize nutrient availability, you increase the efficacy of your herbicide programs. It provides more hospitable conditions for soil microbial life. You reduce your aluminum toxicity, and of course, all of that works together, and also just plant roots have more hospitable conditions, and thereby enhancing crop performance. So why do we care? How much lime to apply is one of the big questions currently resonating on the greater Palouse region. And you'll see a little bit later, some of the work that I did coming in as a new graduate student was field trials that, where we applied lime in the field. And one of the questions that I asked as a brand new graduate student okay, well, how do we know how much we should put down to see if we're, if fluid lime compared to sugar lime is going to work on the surface to address stratified soil pH? Like how do we know how much to put down? And the answers that I got were definitely more driven by, oh, people might be able to afford to put down like 400 pounds, but they weren't really, there wasn't a way that I found in that space at the time to really be able to answer that question with good information based on soil testing. Um, so if we don't put down an informed amount of what the soil needs, how can we truly evaluate the effectiveness of liming in achieving management goals? So that question, how much lime to apply, led me down a whole new rabbit hole that is called lime requirement testing. So this is more complex than looking at starting pH values. I'll show you some figures of that a little bit farther down the line. But I will say that soil pH determines if lime is necessary, but it does not indicate how much lime is required unless you combine it with some other soil test variables and do some math. So target pH is the pH value at which the negative impacts of soil acidity are offset. So this is going to be an individual management decision that's determined by desired crop rotation, your desires for nutrient availability, and your soil health goals. So common values are 5.5, 6, 6.5, and up to 7. And again, that's, we don't have a number for that for a region. That is something that is more of an individual management decision. One of the things that we can keep in mind is this work done by Mahler and McDowell, who you saw in the Schroeder-Finklenberg presentation previously. So here we have the various crops, including you can see varietal effects on from wheat, where you have low aluminum or low pH tolerance versus high pH tolerance response in wheat. But you can definitely see where there's those legume crops do tend to be experience more detrimental effects from lower pH conditions, very likely because of the negative effects on their symbionts environment as well, or those nitrogen fixing partners. Okay, so when I said that you can't determine lime requirement from the pH of the soil, this is why. So I'm not sure how many folks in this audience love looking at correlation graphs, but here on the x-axis we have soil pH, and this is from some of the research we did that I'm about to get into. But this shows what the lime recommendation for a target pH of 6 is. And if you're familiar with R squares, you know that, or if you're not, 1 is kind of the most perfect relationship where all the dots line up perfectly on this line, and so they're very well correlated. But here you can see that number is pretty far away from 1 at 0.5, almost 0.55. And so maybe slightly better than random chance, but you can see that these points associating soil pH with the lime recommendation are not well correlated at all. They're pretty all over that line. So that's because buffer testing, the soil test specifically, buffer testing accounts for the soil buffer capacity and exchangeable acidity that is present in the soil. So exchangeable acidity is the hydrogen and aluminum that is held on the soil exchange sites. So hopefully this is sounding a little bit familiar. Again, from the previous talk, we're building on that. So as Doug previously said, buffer capacity is the soil's unique. The buffer capacity of each soil is unique. It's based on texture, cation exchange capacity, and soil organic matter, and the presence of acidity. So here you can see nutrients on soil, clay, and organic matter sites. It's kind of like a parking lot where all these different ions get to hang on based on their attractiveness to the exchange sites. So hopefully that's clear, but again, that's driven by, clay has a higher cation exchange capacity, so organic matter has really high cation exchange capacity. Sandier soils tend to have very low buffer capacity. So fortunately here in the greater Palouse region, a lot of our soils are silty, and there's a lot of folks that are blessed with very high organic matter. And that's really great. That's allowed us to not to have more time with this challenge. But unfortunately, you're going to see some bigger numbers when you start seeing the lime requirements that came out of our incubation studies as a result of that higher buffer capacity in many of our region soils. So it's a good thing because we can hold lots of nutrients, and again, it's allowed us to, be able to buffer the acidity in the soils, but it does determine the rate of pH decline. So, being able to do that more slowly, but it also determines the response to liming. So one of the things, this is one of my favorite analogies to buffer capacity, is if you have two tires that you're supposed to fill to the same PSI, right? So that's your target PSI. You've got a tractor tire and you've got a bicycle tire. So you're going to have to put a lot more air in the tractor tire in order to achieve the same target PSI as the bicycle tire. And so when we talk about kind of how much lime to apply and how that's different between different soils with different buffer capacities, you can, that analogy between, putting more into the tractor tire versus the bicycle tire, and it's still the same kind of target pH or target PSI. So, hopefully I did justice to that analogy. When I first saw it, it really spoke to me. So hopefully that helps you all out too. So how do we estimate lime requirement? There's a lot of different ways. We can do just spread and measure different rate studies in the field and measure pH over years and see which one works best. There's lab incubations with reagent grade or lab grade calcium carbonate under ideal conditions. And we do we can do different rates, different soils, and better understand what our ideal rates are and the soil's response to different rates of calcium carbonate under lab conditions. With that, you'll hear more about that soon. There's also been some regional exploration into a rapid incubation methodology. There's also titration, also done in the lab. As part of the work we've done, we also explored matching lime requirements to combining other soil properties into that are more commonly measured, such as organic matter, pH, and aluminum, and combining those to better understand lime requirement. And then, of course, there's buffer tests that are a tried and true method across the United States, but again, you'll hear more about those shortly. So you'll hear more, as I said, as we progress. I'll talk more deeply about both lab incubations and buffer tests. So there's trade-offs for each of these methods, and you can combine methods to help verify which ones are going to be most effective for a region's unique soils. And I know that we've got a couple soil test lab folks on this call today, and I think you probably will attest to the fact that soil test labs and also growers and crop advisors and everyone really prefers low cost, high throughput. How do we get the best answers for the least amount of resource input? So, and that's where the buffer tests really can shine. So different buffer tests are used around the United States. So you can see this map here showing the different names for the buffer test. We've got SMP, maybe you've heard of that one, Adams and Evans, Malick, and then there's several others as well. And this is a pretty old figure here. You can see this was put out in 1996. So actually, I think Montana has unfortunately realized their own soil acidity challenges and they have done their own work in buffer test evaluation. So they probably actually have one now that is recommended. In Washington State, the SMP recommendation was done by some work in the 70s over on the west side. So as we know, we have very different soils across our wonderful state of Washington. And whether or not, like, it is very likely that one buffer test may not actually be the right chemistry for the whole state, right? As you know, the mountain range bisecting our state has a meaningful impact on the soil's formations and the way they behave. We also have the basin and then the greater Palouse region. So all having very different soils, including mountains and forests. So yes, buffer tests tend to have their chemistries more uniquely tailored to a certain type of soil in order to, and then calibrated to best predict lime requirement. So, and again, just which tests are suitable varies regionally based on the soils present. So the Idaho recommendation that is in this figure is actually the Woodruff 6 based on the work of Molly, Mahler, and Mohebe in the 80s. So and that was one of the tests that we evaluated. So, and again, Idaho is also very diverse. So is the same test for northern Idaho versus southern Idaho the most appropriate? You know, that's still to be determined. So when we did include some Idaho soils in our work that we're about to jump into. So finding the right tests are essential for good local estimates because these tests were originally developed for specific soils. So the buffer test. So, and then I just have this list of a whole bunch of different researchers who have done regional buffer test evaluations that calibrate for more regionally specific soils. So, and of course, I, as a soil scientist, again, have to have an excuse to put up some nice pet-ons and just to demonstrate how very different soils are. So very commonly you'll find acidic soils in the Southeast, and that's where a lot of buffer tests were developed because that's originally where, you know, agriculture in our country started, and all of the natural weathering that occurred led to naturally acidified soils. So they had to really get right on their Lyme program development. And so that's where a lot of these tests came out of, but they have since spread across the United States and the world, as you've seen. So as I mentioned, early regional work by Mohebe and Mahler recommended the Woodruff Buffer 6. One of the things I wanted to point out from their work, check out that pH range. I think the previous talk also mentioned the pH values that they found in their work. Here, they evaluated soils with pH ranging from 4.95 to 5.91 and aluminum parts per million, not greater than 0.77. So since then, we've had 30 more years of nitrogen applications, changing soil, decreasing pH, and increasing aluminum. So the study so I'm just going to briefly go over the how of the work that we did to try to solve this problem of how much lime to apply and how do we know what's right for our unique soil of interest. So this process started with an identify the soils, collect them, and characterize them process. So and then it moved into the laboratory incubation of different rates of calcium carbonate. I'll go into that a little bit more. And then we tried a bunch of different buffer tests. And then we compared those things to each other to identify what would be the best buffer test to provide lime requirement estimates in our region. So we identified based on soil series. These are all predominant agricultural soils in the greater Palouse region, in the inland Pacific Northwest, all taken from 10 sites. Again, agricultural soils in production that had not been fertilized that's the season. They were collected in the spring. They were both from natively prairie soils as well as native forest soils. So we tried to get a good mix of representation there. Previous talk Doug did reference that is the underlying soil factors, soil forming factors, is thought to influence that inherent buffer capacity and susceptibility to acidification. Though we are seeing that the acidification has been emergent across a variety of different soils despite native vegetation. So this was me as a graduate student a few years ago, out in the Walla Walla area, working with Dr. Paul Carter, who I believe I should photo credit for that one, verbally, if not actually on the photo itself, where I was able to collect some soils from one of his collaborators' sites. So these soils were collected as a composite of the top 6 inches. All of the soils had a pH of less than 5.3. So that top 6 inches was kind of selected as a plow layer sample. Here's a map, or a general map, of where these soils were collected from. So again, we made sure to capture on the Idaho side as well as the Palouse. So then we characterized them. Big shout out to Steve Jones at Best Test for his work helping with all of that. I got to send a lot of soil samples his way during this project. And yeah, as I mentioned previously, we found soil pHs as low as 4.36, and aluminum levels correspondingly as high as 139 parts per million. You can see even with the organic matter rates, 3.5, we've got base saturation of just over 41%. So that base saturation is how much calcium and magnesium are taking up, and I think potassium is in there as well. So how many of those nutrient bases are taking up spots on the cation exchange sites in the soil. So it's a good measure of how much of those nutrients are available and being held by the exchange sites. And that is one of the dimensions of one of the indicators of soil acidity. And we'll hear more about that from Dr. João Antonangelo at our in-person event in Lewiston or Clarkston area and in January. So you can see that they're a bit color coded. So that was a nod to the native vegetation. So green was natively forest, and the yellow sites were natively prairie. So we, again, characterized by clay or by soil texture. So you can get an idea, like these are things that start to get at between the organic matter and the soil clay, and the cation exchange capacity do start to give us an indication of buffer capacity in a way to measure it in other ways as well. So as we progress with this research, so the highest pH we had 5.33, and correspondingly 5 parts per million of aluminum for this study. So after we identified, collected, and characterized, we started into our laboratory incubation. This was an incubation in labeled mason jars. You can see here one of my colleagues' hands helping me out with this study. So we used lab grade calcium carbonate, so very fine, and we calculated out different rates. Definitely looked very different than the rates applied. They're the same, but very different because I was measuring them in very small quantities to mimic very large quantities in the field, since we were working with a smaller amount of soil under ideal conditions in the lab. We made sure to mix that up very well. We kept it at field capacity level moisture for 90 days and room temperature. So really just trying to create the best possible scenario for soil acidity to react with calcium carbonate, again, at rates from 0 to 20,000 pounds per acre, to see the Lyme response by all of the 10 soils. So this was hundreds of jars. And so that was a pretty fun study to conduct, especially because, in science, we love to replicate. So hundreds of jars, but it was very much worth it. We got a great graph out of the deal. So I will show you that shortly. The next thing that we did from a method standpoint was the buffer test screening. So how do buffer tests work? The chemistry of the tests differ, but the overall principle is that it's a mixture of different chemical compounds that start at a higher pH, and then when you add acidic soil, the decline in pH of the buffer solution decreases in a very predictable way. So you can see this figure here that demonstrates the SMP buffer test and how the chemicals that go into it to put it together each contribute different parts of that linear curve, so that as the buffer test decreases in tenths of pH units, we can connect that predictable response to the lime requirement values to give the recommendations. So again, because that chemistry differs, that's part of the increased suitability with certain soils, where they were developed, and then how they subsequently get calibrated on a regional basis. So each test has those multiple calibrations that are used in different regions based on work like this. So we screened the many different tests. We screened the SMP, which has been the longstanding recommendation in Washington State. We also screened Adams and Evans, which I know is practiced by soil test labs here. We also screened a couple different versions of the Woodruff test, since that was what was initially found by Mojave and Mahler to be effective for this region. So the Woodruff solution adjusted to pH 6 as recommended in their methodology, as well as two different variations on the Woodruff 7, because I found a couple different protocols for the Western states versus what's a bit more standard. And we tried the modified Malick and the Sakura. So the last two, one of the kind of challenges around buffer tests is that if you start doing a lot of them, you really have to start thinking about hazardous waste disposal, because one of the ways that they work is using cations, that very attractive cations in the solutions to displace the acidity ions on the soil itself. And so these are things like barium and again, we start to get into some things that are a little bit less fun and much more expensive to be disposing of. So in recent decades, there has been, from the original work done on buffer tests in like the 30s, in recent decades, it's been recognized that that is less desirable, particularly to reduce the burden on soil test labs for that more expensive disposal. So some of these methods use different combinations in the modified Malick compared to the original Malick, and the Sakura test is actually a kind of less hazardous version of the Shoemaker, McLean, and Pratt, or SMP buffer test. So we tried all of these. That picture made it into the furrow. I feel like I'm wearing the wrong color shirt for a Coug, unfortunately, but that's what I was wearing the day the journalist from the Furrow magazine years ago came into the lab to take a picture of me measuring buffer pH. So after we did the laboratory incubation on one side and the buffer test screening on the other, just measuring all our soils with all the different buffer tests, we put them together after determining the lime requirements from each soil. So this graph is one of my favorite from my several years in graduate school, focusing almost exclusively on this research. And this graph is the incubation response of the response to the various soils to the incubation with calcium carbonate under ideal conditions. So this is really the accelerated version of what we might see in the field for each of these different soils. So you can really notice that each soil has its own unique kind of response curve. So in the previous talk, Doug put up the figure that was a more general based on soil texture, just linear response with buffer capacity with different soils. This study actually shows the unique buffer capacity of each of those soils and what those curves look like. So one of the things that I think is interesting is the Santa soil. That was the one with the lowest pH going in, but it actually has a pretty steep slope. So that means that it has a lower buffer capacity. It means that it's going to take less lime to get a higher response or to get up to the target pH. So that's pretty interesting. I think some of the soils like the Larkin have a little bit more just a little steadier of a slope, or this Joel soil, the buffer capacity of that one is pretty high. It's a much more it's a much flatter slope rather than going up like that. So we took these data and cross-referenced this more representative actual lime requirement, represented by putting lime in the soil and seeing what the response is to the different rates. So we took that, the target pH of 6 is what we used when we cross-referenced to the lime requirements recommended by the buffer tests as our validation point. So when we calculate lime requirement estimates from the buffer test, get ready for a little bit of math. I'll try to gloss over it. And if you ever have any questions about how to really get into it, feel free to reach out to me. But for right now, we don't need to go into the lesson on really how to do this math. But there's a couple different ways you can actually do calculations with your buffer test. You can calculate your acidity, and then you can the calibration equations, plug that in, and then you come out with your pounds of calcium carbonate per acre. And again, you want to be aware of, this is for kind of the 6-inch plow layer for the recommendations. But you want to watch kind of the quantity of soil in the profile that is also being recommended. So, and then sometimes there's tables. So the SMP, I think they try to make it more user friendly. So if your soil buffer pH, right, if you start at 7 and then you decrease that buffer pH after adding the acidic soil, if your buffer pH goes down to maybe 6 and your target pH is 5.5, then that's 3.8, and sorry about this, megagrams per hectare of lime required to reach that target pH of 5.5. So that's how those tables work. And again, this is for a furrow layer of 20 centimeters. This is from a soil science handbook. So again, we've got science units in this one, but this is really just for demonstration purposes at this point. So what did we find? When we compared the actual kind of lime requirement values, those are here on the incubation, are on the x-axis labeled incubation lime requirement to target pH in pounds per acre. And then we have the y-axis, the buffer test recommendation, to pH of 6. And so this graph shows the two probably most commonly used buffer tests in this region, the SMP test and the Adams and Evans. And again, if you recall what we were talking about previously when we talked about correlations and the kind of numbers that we look for, the closer to 1 means the closer the correlations. And you can see that neither of these values are very close to 1 at all, with the SMP actually being much worse for Palouse soils than, this is probably, in my experience, not the type of data you would want to base your soil management, especially a very costly soil management decision on, because it really is kind of all over the board in terms of what the recommendations are versus what the soil is kind of actually needing based on the actual incubation. So we can do better. as it turns out. So we did evaluate, as I mentioned, the original recommendations by Mohebbi and Mahler to the Woodruff test. So this is how those worked out. Those correlations actually were pretty good. You know, you start getting into the 0.7s, especially 0.75, 0.78. Those are pretty decent correlations. One of the things though, and I think I might, and I've got this on the next slide, but you can see here, the slope of this line here for the blue line, Woodruff 6, is not very steep. So actually that means that there isn't a wide range of nuance in order to, a wide range of predictions or predictability possible to capture nuance for an individual soil. And then we have the Woodruff 7, had a pretty good correlation, but it did tend to over predict. Like we can see this point here where the buffer test is recommending 8,500 pounds of calcium carbonate per acre, and the actual lime requirement is, 4,500. So I think there's, if there was more interest in the Woodruff 7, a regional calibration just to make sure that we're bringing those over estimates down would be in order. However, we did actually find the modified Malick test to have an R-squared of 0.87. So that's a pretty solid correlation, and actually without any modification to the calculations recommended by this work, it gave a pretty good comparison. So, when the incubation was saying this soil needs 6,000 pounds, the buffer test was predicting that the soil needed right around 6,000 pounds. So that's the kind of thing we're looking for. And then as well as the dispersion of the dots kind of near that 1-to-1 line, and clustered on that slope. So that was a really promising sign. So just for fun, here's a soil test report that I got as part of this work. Here you can see the Malick buffer that was run at my request, and really appreciated that. So here's the calculations that you get to run if you want to make those recommendations. So here we have you calculate your soil acidity, take 6.6 minus what your buffer pH results are, divide it by 0.25, and then plug it into subsequent equations to give you and there's that math that I did out for you all, but that recommended 2.57 tons, or just over 5,100 pounds per acre. And I am sorry about these numbers. I just did the work on them. I know that these are probably not numbers anyone likes to hear. But this is the research results as we found them. So the nice thing about that is when we were and it's a slight over prediction, as you can see, but the incubation lime requirement for that soil was 2.3 tons, or almost 4,800 pounds per acre for those top 6 inches. So that's about as good as we're going to get in these lime requirement estimations. So with that, let's see, I've got a little bit more time. I'll probably take 10 minutes. I might gloss over a couple of the slides at the end. But in any case, to wrap up this piece on buffer testing for determining lime requirement for the greater Palouse region, the modified Malick was the most effective at predicting lime requirement on the greater Palouse soils. The Woodruff test, as I said previously, could also provide effective estimates. The overprediction with the Woodruff 7 has some potential with further region-specific calibration if for some reason the modified Malick was found to be undesirable. And based on this work, the Woodruff 6 buffer pH range that came out of the testing ranged from about 5.4 to 5.66. So what I would like to see when being able to really determine effective Lyme programs is more room for capturing, a couple 100 pounds of difference, because that's real money. And that range of 5.4 to 5.66 really gives a lot more coarse prediction, or course estimates for your lime requirement. And so I'm not quite sure what to do about that, but that did make that, in my mind, a less favorable test because we're just not able to capture the nuance in those recommendations. Okay, so this was also a fun calculation. So based on that I thought it'd be nice to share with you all today. So when we did the incubations, we did all the different pH values at different rates, or we found all the different pH values that resulted from different rates. So based on that, this table shows the starting pH over on the far right, and how much lime is required to get to a target pH of 5.5, 6, and 6.5. So just very roughly speaking, it seems to be about 2,000 pounds on average for each half of a pH unit increase from that table. And again, for all of this work, we did use that target pH of 6. So this is what you saw the graphs of what that was compared to, but these are the actual values for each of the soils. But again, the beauty of the buffer test is that you can put it on any of these soils, and in what is going to be the best predictor of the range of soils for our region, kind of in aggregate and as individuals. Hopefully that's come through in this talk before, and I'm always happy to have further conversations about this if you guys really get excited about soil testing and soil chemistry. Okay, so another component of the work we did that I'm just kind of throwing in because it's interesting. This is all unpublished at this point, but this is from some work with some gracious collaborators, letting us do some work on their ground up in the Rockford area. So in the fall, lime was applied in the field at different rates in the fall of 2013. And actually, I'm going to give a shout out to Kurt Schroeder because he was instrumental in helping, in particular, apply the fluid lime with the cool little sprayer and special nozzles to get that out. So we applied a range of course, we did controls, but we applied a range of 400 pounds per acre of the fluid lime, and that was available at that time. So I understand the formula has changed a little bit in the meantime. And then we also compared it. So at 400 pounds per acre, we had both fluid lime and sugar lime. And then at the 2,000 rate, 2,000 pounds per acre, which was the highest rate we did at that time, because the buffer test work was yet to be done. We had 2,000 pounds per acre of the fluid lime and the sugar lime that we're comparing in this work. So please do keep in mind that pH changes shown at the top point probably is as much the result of compositing the soil samples in the little cup in the lab, which is why we did 2 centimeter increments, which is about 1 inch. So these figures Doug showed more comprehensive soil profile. We did take soil samples down to 30 centimeters, but in this stratified soil acidification work that we were looking at, we did focus on about the top 5 inches as capturing that the acidified fertilizer zone in this system. So one of the things that I thought was most interesting is that we did pull and test soil cores from the actual forest soil. And so you can see here that at the surface that had a it had a pH of about 5.5 and went up from there, versus the control soil was over here in the orange. I'm not sure why it's higher at the top versus this the treatment with sugar lime that is actually a bit lower in the very first data point, but both of them got below, but you can see that soil is below 4.5, regardless of the treatment, especially that first year, because we did not see a whole lot of actual treatment effect that within 1 year of having applied those rates of different limes. And so you can also, here you have the KCl extractable aluminum in that native forest soil. And that is still forested. You have almost no aluminum versus check out this x-axis here where, you know, you're getting some pretty high aluminum up in that area. And then also base saturation. Again, this is how much calcium and magnesium are on those soil exchange sites in lieu of acidity. So, and again, as you get into that stratified zone, those numbers start to get pretty low, especially when compared to the forested soil and what you see under the natural conditions that have not been fertilized. Okay, so what happened when we applied these different rates of lime? Again, I'll keep this pretty quick. So by the spring of 2015, we have this native prairie soil just outside of Pullman at the Palouse Conservation Field Station. You can see the pH rates, and sorry, I did not convert the science units, but again, it's still that 400 pounds per acre compared with the 2,000 pounds per acre of both fluid lime and sugar lime. So you see our site outside of Pullman versus at the Rockford site, where after 2 years, or about a year and a half under the lime, or 2 winters, let's go with 2 winters of ability of the soil to interact with the lime applied, both fluid and sugar lime. The rate did seem to matter more than what actually was applied, but both had pretty fine particle sizes. In this case, we did not use crushed limestone as a comparison. I think you'll see more of that work with Dr. Schroeder's presentation on January 18th. And we started to see some potential effects after those 2 winters at getting down to about 2 to 3 inches. So that's kind of because calcium carbonate, it's a rock. It's not terribly reactive. Ultimately, that is what we're working with in this situation. And unfortunately, and it's, as I've said before, it's a rock. It is on geologic time. Unfortunately, it is less on agriculture time. And that is one of the challenges and things to keep in mind as, you know, you think about possibly developing a lime program. And that is a challenge to figure out, I think, as part of this work. So just to show you, the aluminum was also reduced by the highest treatments of lime with the stratified conditions. I am just really, the difference in the x-axes in these conditions is something I think worth noting. So again, this was in the spring 2015, after 2 winter seasons of the lime being in the field. Okay, so again, I'm just going to really quick go through this. Applying lime, there's a lot of different methods to do that. You can do fluid or dry surface application. You can incorporate. That's often a crushed limestone or sugar lime. There's prilled pellets. Those can be moved through different types of equipment, and you can do precision application. Really looking forward to hearing more from Dr. Casanova in the next session about being able to identify across the landscape, but and where the heterogeneous soil acidity might be, and identifying that, but also keeping in mind that, you know, as I just talked about, precision application can also happen through the soil profile. So there's some other work being done at the Cook Agronomy Farm that hopefully in another year or two we'll get to hear about that at a subsequent update on regional soil acidity type of event. So all these different methods have their trade-offs. So again, buffer tests determine how much pure calcium carbonate to apply, not how much lime. All of these different materials have different, the presence of calcium carbonate in these different materials varies based on the product. And so you want to make sure you're doing your understanding how much actual calcium carbonate is in a product and doing the math to make sure you're getting the right rate of calcium carbonate to match your buffer test lime requirement estimate. Okay, and it's also, of course, been noted already that finer particle size does increase the reaction time, or does decrease the reaction time. So that's the fineness factor. So the smaller the particle size increases the lime reactivity. And please do go ahead and check out the Small Grains website and the Soil and Water Resource publication. There's a lot of different materials that we worked pretty hard as a team to put out for all of you to hopefully benefit from. One of the things that's on there that I think is going to hopefully be looked at again, because it's been out for a little while and I think was put out before this work was done, is the Lime requirement calculator. So this is what that looks like. So all of the math that I just showed, it helps to get you out of maybe doing some of that. So when you're looking at lime, you want to make sure you look at the calcium carbonate equivalent. So that's the purity. Also, there's the fineness factor and the lime score. And those all go into understanding how much lime to apply. So your effective lime program depends on your management goals, considering your nutrients, the crop rotation you want, your herbicide efficacy, and your soil biology. Those are all important components, with pH underlying as a master variable and with soil health in mind. You want to do it at the right rate. pH does not determine the lime rate. Not all tests give the best estimates. And you want to make sure you're calculating based on the calcium carbonate in a product or the magnesium carbonate. So really the key there is the carbonates, as we saw in those initial cartoons. The right placement and understanding your favorite application method and system, and really thinking about your product and finding the thing that works, finding what works for you in terms of method, cost, purity, and reactivity. So with that, I want to acknowledge all of the people who helped inform this work. It was definitely not work done in a vacuum. And again, really wanted to acknowledge, there's Steve and Paul and Dave and all of my lab mates and Tabitha Brown and of course the Washington Grain Commission for funding this work. Again, please do keep in mind, if you care about this work, help get more of it funded, because regional problems need to be addressed. And that's one of the best ways that we can keep moving this kind of thing forward, because they already have liming programs other parts of the world that are not tailored for our region. So with that, just a couple of fun pictures from agriculture in another part of the world. This is all in Southern Africa. And I want to say thanks for bearing with me.